This is lecture 6 on the theme of the formal rules of quantum mechanics. It's a mathematical physics course called Quantum Mechanics at senior level. The first author of the text that I'm using is Davies, and here's the book. It's called simply Quantum Mechanics, the second edition. There are two authors, in fact, but I usually just say the first author for classification reasons. So Paul Davies and David S. Betts. Okay, so this chapter is in fact the largest in the whole book. It's 22 pages, followed by the next chapter on angular momentum, which is 20 pages. And then the rest are just around 10 pages or less each. So this next chapter are, in a sense, the core, the heart of the course, with a lot of theory, the basics of quantum mechanics. And so what we'll be doing, in a sense, we'll be summarizing to some extent. We've been talking about various principles of quantum mechanics, uncertainty principle and superposition and so forth. So in this chapter we'll be sort of tying it together, and then with certain advances based on the formalism that we create in this chapter. Now the formalism, personally doing quantum mechanics, the formalism introduced in this chapter is the one I'm used to. It's the one most physicists use. So just a minute, I forgot to switch off the fan. That might change the noise level. Sorry about that. Right. So what we need to do is create a fuller version, a more comprehensive version of quantum theory, because for example, we don't yet have a quantum theory about measurement, and in fact the measurement problem is still just that. It's a problem. It's one of the major topics in the interpretation of quantum mechanics. That's still a problem, right? But we will devise this chapter, this lecture, a theory of quantum measurement. So that's sort of what this section is saying. So in a sense you can say this session starts the process of writing down, in a sense, the postulates. Like if you have a logical system, or a mathematical system, you have to start with something, some basic postulates that you postulate, that you just simply you assume are true, and then you make the deductions from those postulates. So in the sense of formal rules, other textbooks would talk about the postulates of quantum mechanics. Essentially the same thing, right? So one of the first concepts of quantum mechanics is the notion of superposition. Like if this psi1 here is a solution to your Schrödinger equation, and then you have a second solution, say psi2. Now because the Schrödinger equation is a linear equation, perhaps I should have written that down. So if you have some operator L that operates on two wave functions, so the sum of them, that will be the same as L psi1 plus L psi2. Now if you have that property for two separate solutions, psi1 and psi2, that the L of the sum is equal to the sum of the L's, so to speak, then the equation L psi is linear. Right? That's the condition of linearity. Now the Schrödinger equation is linear. So that means if you have two separate solutions, psi 1 and psi 2, then you can add them with certain weightings. Now these C's here are just complex numbers. This symbol here, it's from mathematics. It's a sort of capital C. It just means the set of complex numbers. And then, well, you know, this one belongs to. So these two numbers here belong to the set of complex numbers. In other words, these two numbers here are just ordinary complex numbers. Okay? So if these two are separate solutions, then the weighted sum, weighted just means you multiply by these complex numbers, so the weighted sum is also a solution. Okay? Now if you can do that twice, I mean if you're adding ones, so if you're adding two solutions, well you can add, well, effectively infinite number, right? So you've got this sigma here, the sum of an infinite number of weighted sums, right? You can have psi 1, psi 2, ... to infinity. So this idea of superposition is really basic to quantum mechanics. Now, mathematically, this is pretty easy, right? Conceptually, that's not a problem. But physically, if you really start thinking hard about what does superposition mean physically, what's going on in the real world that these solutions can add in this sense. Like, I mean, one of these solutions might be a wave going this way, and another one might be a wave going the other way. Are you talking about two different waves? Are you talking about the same wave? Yeah, there's all kinds of interpretive, philosophical problems about quantum mechanics. And later, once I get through the core courses, I plan to give many, not just lectures, but courses on the interpretation of quantum mechanics, because it's a fascinating and very important subject. But since it takes me about somewhere between 1 to 2 months to camcord just one course, I have to be careful about my time. So I have to prioritize. So I talk about core, heart, basic courses first, starting with the undergrad courses, about a dozen of them, and then move on to graduate level, M1, M2, first year master's level, second year master's level, PhD 1, PhD 2. Right? Okay. So one of the new ideas we'll start in this session and continue for quite a few sessions is the idea of representing, talking about a wave function as a vector. So one of the revolutions that took place in the mathematics of quantum mechanics in the 30s was by John von Neumann.